Hi, I'd like to introduce the concept of Coulombs Law. Now, Coulombs Law is the fundamental electrical force law for charges interacting with other charges. And for any system where we have two electrical charges, there's a force felt between those charges that is proportional to the charge on each object. It's proportional to 1 over the distance between those two charges squared, and we need a constant of proportionality to get units of force from units of charge squared, which would be coulombs squared, divided by units of distance squared, meters squared. And that constant is named for the discoverer of this law, Coulomb. And what Coulomb determined was the force between charges is equal to the constant times the value of charge 1 times the value of charge 2 divided by the distance between the charges squared, acting on a line from charge 1 to charge 2. Now, direction in that is very, very important because charge can be positive and negative. So if they're both positive, then that force from 1 to 2 would be pushing 2 away. And the force from 2 acting on 1 would be pushing 1 away. Now, if we were to have two negatives, the same thing. Negative times negative is positive. 1 pushes away 2, 2 pushes away 1. That explains the sort of basic static electricity rule that we learned from an early age, that like charges repel each other, and if I get a positive and a negative, that means 2 would be pulling on 1, 1 would be pulling on 2. Opposite charges attract each other. Now, Coulombs constant is itself made of other constants. In more sort of modern structures of physical constants, Coulombs constant is equal to 1 divided by 4 pi and a quantity epsilon naught that we call the permittivity of free space. And we'll talk more about the permittivity of free space as we get into some later chapters, but it's related to space's ability to store energy in the form of an electric field. Well, if I take the value of epsilon naught, multiply by 4 pi, and invert it, I get a value of 8.9876 times 10 to the plus 9 newtons times meters squared over coulombs squared. Now, one of the things that was observed with the structure of Coulombs law, almost instantly, the structure of Coulombs law looks a lot like the structure of Newton's theory of gravity, where we had a mass times a mass over a distance squared, and we needed a constant to make our units work out. There's one big difference. And in Newton's theory of gravity, Newton took for granted that the gravitational mass and inertial mass were the same thing, and if inertial mass is the amount of stuff, that's always positive. And mass attracts other mass gravitationally, which means the gravitational force is always attractive. The electrical force can be attractive if we have opposite electrical charges, or can be repulsive if we have like electrical charges. So that's one and probably the biggest difference between electricity and gravity. And there have been efforts pretty much since Coulomb's structure of Coulombs law came out to try and find out, are there more fundamental similarities between gravity and electricity other than, ooh, hey, that's neat, the equation looks kind of the same. And that work is still continuing, because one of the really interesting questions has to do with gravity and gravitational mass. Can it be a charge, and can it behave like a charge? And that question will get really interesting in our last chapter as we talk about the standard model of particles, talk about antimatter, and talk about some aspects and big problems in cosmology. But apart from thinking, well, at some point all physics should inherently be unified, we still don't have a concrete structure to take all of the physical forces and bring them together into a single, complete, coherent theory that works at all scales of size, time, and energy. But that's one of the exciting things about theoretical physics, is there still are questions out there to answer. Now, one last thought with the Coulomb force. Like all forces, it's subject to the rules of superposition. So if we have dozens of charges, we could find the total force on our first charge by summing up all of the forces from each other charge acting on that first charge. So what we would do is take the sum from whatever our second charge is to our nth charge of Coulombs constant times the first charge that we're dealing with times the second charge divided by the distance from our first charge to our second charge squared in the direction from, technically, if we're looking at the force on the first charge, it would be from that second charge through that nth charge acting on our force. Now, in practice, this is not as doable as it is in theory. Because in practice, even though charge is quantized, all charges are made of a countable number of electrons or protons in ordinary matter, we're usually dealing with Avogadro's number of the things, and we just can't count that much. But in the smaller scale, if we only have 4 or 5 charged objects that we're dealing with, then this is a framework that may be doable as long as we're careful and remember we have to take into account direction. We're doing vector sums, so pay attention to any direction, relative direction between those multiple objects. Thanks for watching.